So we're going to work through one more in class. I'll work through one, and then I'm going to have you work on some. So let me. I'll go ahead and hand these out while you're getting ready for class here. So we're not going to work on this until we finish the one I'm going to do here. It's a trig example. And for some reason I don't have enough copies. I don't know why that was. Well, I think I do. No, I don't. Okay. So I may have to run over and make some more copies. Let me just see how many I need to make. I don't know what happened. Maybe the copier stopped in the middle of it. Okay, so I need 1, 2, 3, 4, 5, 6, 7, 8, 9. Asia comes. Okay, so let's look at this problem. So the basic idea is we're going to find where we have minimums and maximums, and so we're going to use the first derivative to find out possible points of minimum maximums by finding the critical numbers, and then we'll use the first derivative test by completing the table to find out if there are any of those critical numbers change from concave up to concave down or concave down to concave up. And then it says use a graphing utility to confirm our results. So we're just going to plot it and see what happens. So in this case, we take the, let's turn this thing off. So the first thing you do is to find the critical numbers, you take the first derivative. So the derivative of the sine is the cosine, and the derivative of the cosine is the sine, or negative the sine. So that's the first derivative. And then we, oh, forgot to put x here. So the cases where you have critical numbers is where the first derivative is 0 or it's undefined. Well, because the cosine of x is always defined and the sine of x is always defined, the first derivative is always defined, so we don't have to worry about any cases where it's undefined. We just have to find the values of x where this go to 0. So we're going to say the square root of 3 cosine x minus sine x equals 0. So thinking back to your pre-calculus days, how do you think we might solve for the values of x where that is true? Up to this point, we've had sines or cosines and we've factored it, but in this case we haven't. And you have to be able to get it in terms of one trig function. So it has to be in terms of the sine. Well, I guess theoretically, if you could factor out a sine or a cosine, if you had a common factor like the sine of x, you could factor that out and then have that part. So anybody have any thoughts? So is there a trig function that involves the sine and the cosine in terms of its definition? So it's not the sine or cosine, that'd be redundant. Tangent, cotangent, secant, cosecant. Well, the secant and the cosecant just involve the sine and cosine by themselves. So it's either got to be the tangent or the cotangent. So what you would do is you would make this in terms of the tangent And you can do that two ways. You could divide by the cosine of x, or you could say the square root of 3 cosine x is equal to the sine of x, and then divide by the cosine. So you get the square root of 3 equals the tangent, well, equals the sine over the cosine, which is the tangent. You could do it in terms of the cotangent if you wanted to, but so now all we have to do is figure out what values of x is the tangent equal to the square root of 3. And that gives us the x values, which will make the first derivative equal 0, which is where the critical numbers are. Oh, I'm trying to get rid of that thing. I don't know why that won't disappear. Let's try it. There we go. Okay. As a sidelight, since nobody gave me the answer here, I'm going to give you a little review here in terms of trigonometry, or trig. Sometimes we've had this case where you've had something like 4 cosine squared of x minus cosine of x minus 1 equals 0. In this case, what you do to find the solutions is you would factor that. So instead of, and you can think of it as 4x squared minus x minus 1 when you're factoring, and then just put x back in for cosine of x, back in for x. So that's one situation you might run into. The other example if you had is something like the sine of x plus the sine of 2x equals 0, say. In this case, again, this one's got an argument of 2x, this has got an argument of x. So what we do is we use one of the trig identities to rewrite this in terms of the sine. There's a trig identity involving converting the sine of 2x to x, and I must have left my, oh, here it is. Yeah, so we look at a trig identity, there's the sine of 2x actually is 2 sine of x cosine of x, but then we could factor out, for example, this one, we would use the trig identity that says the sine of 2x equals 2 sine x cosine of x equals 0. And then you have this common factor, so you could factor out the sine of x. So you'd have sine of x times 1 plus 2 cosine of x. So you'd find the solutions where sine of x equals 0 and where 1 plus 2 cosine x equals 0. So that's one. That's another example. Let me think of another one. There's like this, where you have one part's cosine, one part's sine. Then you can convert it into the tangent. And then you can use the things we've learned so far. What other kind of things happen? That's all I can think of right now, but I'm sure that when I think of more, I'll let you know. Okay, I'm trying to delete this thing. Okay, so let's put that on one page. Maybe I can delete it now. There we go. Okay, so the question is, where does the tangent of x equal the square root of 3? And again, in this case, you could use the unit circle because this is one of the cases. So why don't you, let me think about that for a second. See if you can solve it using the unit circle, and then we'll solve it using the reference angle just to show you how. The reference angle, you don't have to think so hard. You just follow the procedure. But think about, if you remember, there's two things you have to think about. Which quadrants is the tangent positive? Positive, okay. And then you have to remember that the tangent is the sine over the cosine. So it's not going to be the tangent of pi over 4 or some similar type angle is equal to 1. So it's either got to be pi over 3 or pi over 6. Just process of elimination, since I told you that this is one of the special angles that we dealt with. So let's take a vote. instead of asking somebody specifically, how many people think the tangent of, and we're just talking about the first quadrant, how many people think it's the pi over 6? Okay, how many people think it's pi over 3? Okay, why do you think that? Zane? What's that? Because they raised their hand, you figured they knew what they were talking about? Okay, I guess that is a truthful answer. Okay, Michaela, you said right. Margaret raised. Everybody watched for Margaret, huh? See, I told them that's. What did Evan? What did you do? Did you raise your hand too? Yeah. Okay. So they just looked to see what Margaret and Evan did. Okay. Um, so I'll have to ask you guys. So you didn't have anybody to look to. So Evan, why is it pi over 3? Evan, why is it pi over 3? Because it is. You just remember that. Okay. So, but yeah, that's also a valid result. Okay. A valid answer. Okay. So if you think about it, the tangent of 0 is 0. Okay. You should remember that one. And the tangent of pi over 4 is 1. So if you think it's increasing, as you increase the angle, it's increasing. So is the square root of 3 greater than 1? Yes, okay. The square root of any number greater than 1 is greater than 1. The square root of any number less than 1 is less than 1. Okay. So because there's a couple of ways you can think of it. Okay, this one way is this way. So if the square root of 3 is greater than 1, then the angle has to be greater than pi over 4. Well, pi over 3 is greater than pi over 4, but pi over 6 is less than pi over 4. So you can do it from an order of magnitude standpoint, remembering that hopefully, Evan knows that the tangent of pi over 3 is the square root of 3, but not everybody remembers that. But hopefully you remember that the tangent of pi over 4 is 1, because that's a nice simple number. Okay, that's how I would remember it. So that's one way. Okay, the other way is you can think about, if you don't remember the tangent things, you probably remember the sine. You might remember the sine things. So the two options, since it's not 1, it's either going to be pi over 6, and the sine of pi over 6 is equal to 1/2, and the cosine of pi over 6 is the other thing that you memorize, which is the square root of 3 over 2. And for the case of pi over 3, the sine of pi over 3 is the square root of 3 over 2, and the cosine of square root of 3 over 2 is equal to 1/2. So to get square root of 3, and I either have to divide this by that or that by that. Well, actually I have to divide, in both cases I divide this by that. And you can see if I divide the square root of 3 over 2 divided by 1/2, the 2's cancel out, and I get the square root of 3. So that's another way of kind of figuring it out without memorizing it. Another way to think about it is, again, if you drew pi over 4, that's this, and if pi over 4, if you drew pi over 3, that goes about here. And you see that the sine, in which is the y-coordinate, is greater than the x-coordinate, which is the cosine. So if this is greater than this, then the ratio is greater than 1, which gives me the square root of 3. Okay, so there are a lot of different ways to figure it out besides just if you forget it. So those are just a few little things that you would get. So what we've figured out the answer is pi over 3 using the unit circle. So then you answer this question: which quadrant is the tangent positive? So we'll ask that one question. Okay. So Jacob, in which quadrants is the tangent positive? Yeah, and that's because it's a ratio of two. It's a ratio of sine and cosine, and the sine and the cosine are positive in the first quadrant, and the sine and cosine are negative in the third quadrant. So when you take the ratio of same signs, you get a positive result. So that's true. So this is our first quadrant solution is pi over 3, and our third quadrant solution is just going to be equal to So our third quadrant solution is pi plus the reference angle. And the reference angle is this pi over 3. That's your solution in the first quadrant. So you get pi plus pi over 3, which is 4 pi over 3. Okay, so that's how you would do it without using your calculator. Now, to do it using your calculator, just in case this wasn't some nice thing that you remembered or memorized, what you do is the steps is you, in this case, you say, and I'm going to use theta again instead of x because I like theta. So tangent theta equals the square root of 3. So we're trying to figure out what values of theta to make this happen. So the first thing we do is we find the reference angle, and the reference angle in this case is the inverse tangent, not the inverse sine or the inverse cosine, but the inverse tangent of the absolute value of the square root of 3. And if you do that using your calculator, so let me make sure it's in degrees because we keep switching between physics and calculus these days. Okay, so we take the inverse tangent of the absolute value of the square root of 3, and we get 1.047 radians. Then you convert that to some decimal of pi, so we take 1.047, divide by pi, multiply by pi, still radians. This is the calculation we do on our calculator. So we divide that by pi, and you get 0.333 pi radians, which is pi over 3. Okay. And the rest of it we've already really done, because for the tangent to be positive right here, the solution is either in the first quadrant, so the angle is equal to the reference angle, or if it's in the third quadrant, it's pi plus the reference angle. Okay, so there we've solved now for the values of x where the derivative equals 0, so we make our chart up here, interval x, f prime of x, comment, and the other day I added that extra line, so let me go ahead and do that, the extra row. So I'm just going to sketch it in. That's just to draw a line. Okay, so the interval in this case is from 0 to pi over 3, from pi over 3 to 4 pi over 3, and from 4 pi over 3 to 2 pi, because the original problem said in the interval from 0 to 2 pi. So now we have to figure out a value of x that's in these intervals, and you might as well pick one that's easy to evaluate. You could use the unit circle if you wanted to. So I'd use something like pi over 4 here. I guess with a calculator it doesn't really matter, but it's, sometimes it's hard to figure out what the decimal, you could calculate the decimal equivalent and choose it in there. But so I'm going to choose pi over 4. I'm going to choose pi, which is between these two, and then I would choose 3 pi over 2. So those are my x values, and then I can go and calculate f of x. So let's take this equation, which is, okay, I'll just copy it over here. So what we want to do is find out what f prime of pi over, or f of, sorry, not f, yeah, f prime. So actually what we don't want the function, we want the derivative, so sorry about that. So back over here, where's the derivative? Here it is. So this is what we want. Group, there we go. Copy, put that over here. Okay, so we're going to evaluate the derivative at pi over 4, that's some number, f prime of pi, that's some number, f prime of 3 pi over 2. That's some number. So plug those in your calculator. See what you get. Remember to change your calculator to radians when you do that. I'll rely upon you guys to give me the answers. I won't actually do it. I'm anticipating that you'll get plus minus plus or minus the other way around, whichever, minus plus minus or plus minus plus. But doesn't necessarily have to be that way. But and again, we're not worried about, ultimately not worried about the magnitude. We just care whether they're positive or negative. But go ahead and figure out what the numbers are. So I heard some of you say you're going to Dabney Day today. Is that true? And you can just do it as a decimal. Don't worry about it. So. I almost plugged it in f of x instead of f prime of x. Let's try that again. Jeez. Oh, no, that's not true. Okay, so what did we get here? Kathy. It's what's the actual number? How about on this? Anybody else? What'd you get? I got 0.517. Is that right? Yeah. So it's positive. You're right. And that's all you really need to know. This is negative. The sign of pi is going to be 0, and this is going to be -1. So you get the square root of 3 times -1, so it's negative the square root of 3. And I got 1 for this, which is positive. So you see it does go positive, negative, positive. So we stick those in our table. So positive, negative, positive. When it's positive, it's increasing. When it's negative, it's decreasing. When it's positive, it's increasing. So if we draw little lines here, you see that we have a maximum here because that's the top of the hill, and we have a minimum there because it's the bottom of the hill. So let's verify that we did this right by plotting it. So we plot the original function, which is the square root of 3 sine x plus cosine x. Square root of 3, oops, didn't like that. I don't know why, okay. Square root of 3 sine x plus cosine x. Is that right? Let me make sure I did that. Yeah. Okay. So we want to go between 0 and 2 pi, and we'll go between -2, +2. We'll graph this thing. So there it is. So you can see right here, which is let me put it in terms of pi. So it's 0.33 pi, so that's what we said, first quadrant solution, and it's a maximum. So we saw here at pi over 3 that we went from increasing to decreasing. So here it's increasing, here it's not doing anything, here it's decreasing. It decreases all the way to 4 pi over 3, which is right here. And then after 4 pi over 3, it's increasing. So that all agrees with what we had in the graph. Okay, so for you guys who have the paper, go ahead and start. I'll go ahead and make a copy. I think there's a copy machine in this room. I've just got to figure out where I put the extra copy that oh, here it is. Okay, so I'll be back in a second. Okay.
I don't believe he has one.
Where is he? Disappeared.
I think he went to the bathroom.
Yeah.
Yeah.
Oh, there he comes. I'll give you mine in just a second. I just need to write something down. Let's see, I'll write it on here. So we got some new Christmas music for my brass band last night, and the one piece was the most famous part of the Nutcracker, and I'm trying to remember how that goes. I was going to sing it, but the most interesting thing was it had 30-second notes. Have you guys ever played 30-second notes? Yeah, no, that's yeah. So it's like a run of 4 30-second notes, and it goes almost an octave. So not only is it just playing 30-second notes would be hard enough, but playing da 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 da, that part, diddle-la, diddle-la. It just sounded like blah 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 blah. I think we're going to have, that one will not make it in the final cut. Did I assign the homework from this section? Okay, I thought I did. Okay, so you guys, the only thing you got to be careful about on this first problem is that when you evaluate the first derivative, you need to make sure that the first derivative involves a negative sign with the highest order term, because you can change it. You can once you set the first derivative equal to 0, you can divide by a negative number and make the coefficient in front of x squared positive. But when you're actually looking at concave up or concave down, you have to use the version of the first derivative that has a negative 3x squared in front of it, not positive 3x squared. You'll get the correct unit. I mean, you'll get the correct roots if you divide by -1 or multiply by -1, but you won't get the correct slopes in the intervals. That's where people make the mistake. So I'm going to, since most of you had a head start, I'm going to just start here. So when you evaluate the first derivative, use this, okay? Because I could, what I'm saying here is when you set it equal to 0 like this, and you divide by -1, if you wanted to make this a positive coefficient, both of these equations have the same zeros. So some people tend to they go back and use this one because it's positive, but you have to go back to this one, which is still negative. Otherwise, you'll get the wrong. It'll be concave up. I mean, it'll be increasing. You'll say it's increasing, but it's really decreasing, and the other way around. Okay, did I do it right? Yes, hopefully, but not necessarily. So, yeah, when you got to this part, you had to use the quadratic formula. And I could have either used this form or this form. I just like a positive first coefficient. So you plug it in the quadratic formula, you get this, plus the square root of 112 is 4.097, and minus the square root of 112 is 0.569. So that's how I broke the interval up. I chose numbers within those intervals so that you can always use 0 somewhere unless it's a critical number, but in this case it's not. So I use 0, 1, and 5. You plug those into the first derivative and use the one that has the negative coefficient out front, and you see that you get minus plus minus, which is opposite that we had before, where we had increasing, decreasing, and increasing, and that's because for this third order polynomial, because of the negative sign in front of the x cubed, it starts up here and then it comes down and then it loops like that and then it goes. So it's decreasing first and then increasing and then decreasing. So I always put one of these on the test. It's either going to be positive in front of the x cubed, or it's going to be negative in front of the x cubed. So you should know what you're supposed to get. You know the answer. You just have to prove why it's the case. Okay. What other questions were there with that problem? Did I answer all the questions? It said something about finding. Yeah. Okay. So it says calculate the values. We did that. Oh, calculate the values of the function or f prime of the critical numbers. Actually, I want you to calculate the value of the function of the critical numbers because f prime is going to be 0. So find the value of the function. Find the x-intercepts of the original function, and it turns out the roots are integers, so you should be able to factor that initial equation. So this is a little review here from pre-calculus. So the first thing you're going to do is basically find the magnitude of the minimums and maximums. We're going to have a minimum. We're going to have a minimum here, but we don't know what it is, and we're going to have a maximum there. So plug into the original equation. So what you're going to do is you're going to do f of 0.57, and you're going to do f of 4.1. I rounded off a little bit. Plug that in. So that'll be negative 0.57 cubed plus 7 times 0.57 squared minus 7 times 0.57 minus 15. And do that also for the second value of x, the second critical number. So you'll have negative 4.1 cubed plus 7 times 4.1 squared minus 7 times 4.1 minus 15. Okay, figure out what those numbers are. And we'll use these two things that we're doing now to help draw the graph once we get that all done. So that's what that part is asking. And the next part is finding the x-intercepts for this equation. So to give you a little review here, what you're going to do, because they're going to be integer values, because I told you they were, they're either going to be plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15, just because those are the factors of 15. And Mr. Pell told you this, I remember because I've seen in his tests. What number should you always try as your first when you're factoring third order polynomials? What's your first guess? Not 0. But what's that? Do you hear somebody? Anybody else? It's plus or minus 1, right? You always choose the easiest one. So you'll use synthetic division. Try out positive 1. Try out negative 1. See if you get a 0 remainder. And I'll do one of them for you as a demonstration. I'll pick one that I don't think it's going to happen. Well, I have no idea what it is, so I don't remember. So let's put a little. So you can do those calculations. Then what you'll do is you'll set up a synthetic division problem. You'll have -1, 7, -7, -15. So if you think one of the x-intercepts is x equals, say, 5. I don't think it's 5, but we'll see what happens. It probably is. So what you do is you take the value that you think is the solution, and you put that here, 5. Bring that down, -1. 5 times -1 is -5. Add these two together, you get 2. 5 times 2 is 10. I think I'm going to get the answer. Maybe, yep. Okay, so it turns out this is one of the solutions. Well, I got unlucky by getting the right answer. So you add these two together, multiply that, and you get 0. That makes it so much easier for you guys. But you know, there's only 8 choices, and 3 of them. So 3 out of the 8's going to work. So I just happened to, it's 50-50 chance that happens. I should have chose 15. I knew 15 wouldn't work. So what you end up with is what you have, the other factor is -x squared plus 2x plus 3 equals 0, or x squared minus 2x minus 3 equals 0. And if you should be able to factor that. So we know one of the x-intercepts is this, and we get the other 2 x-intercepts from that. And once we have the critical numbers, the value, the function of the critical numbers, whether it's a minimum or maximum, and the x-intercepts, we're going to be able to draw a pretty decent curve of that third-order polynomial. So I'll ask you guys what you got when you plug the function value in here. So at least give you guys something to do. That's too nice. Okay, so let's see. Who am I going to pick on? These people are still putting stuff in their calculators. So if you want to look like you're busy, so I won't call on you. Start pushing buttons on your calculator. Okay, so you've done the factoring. Oh, what did you get? Did you get values there? -16.9 and 5. Okay. Let me just take those. So hopefully Lexi's correct. Somebody verify. So she got -16.9 and 5.1-ish. Is that right? Did she do it right? Good. Okay. So so now what we can do is we can plot the graph. So you've got the piece of graph paper there. So let's do that. So we're going to add a page, and we're going to get a piece of graph paper. Looks just like yours, because that's where I got it from. Okay, so here's my piece of graph paper. So let's see what the so the zeros, the x-intercepts were x equals 5, and if you factor this, you'll have x minus 3 and x plus 1. And so you'll get x equals 3 and x equals -1. So those are the 3 x-intercepts. X equals 5, so put a little dot there. X equals 3, which is right there, and x equals -1. Then we have we also have the y-intercept, which we haven't done. Let's just do, that's always easy. The y-intercept is -15. So when you set x equal to 0, you'll get -15. So let's write that down as well. So the y-intercept, that's when x equals 0, and you get y equals -15. So we're going to plot that. We're going to have to adjust the scale a little bit. So let's make it so that we go from -20. Is that going to work out? Yeah, -20 to +20 here. will go from -10 to +10 on this axis. So it says that the y-intercept is -15, which would be right, let's see, there's 10, 12, 14, 15 right there. So that's the y-intercept. And then we know that at x equals 0.57, which is right here, we're -16.9. So that's -16, -16.9. So that comes from this point. And we also know that at 4.1, which is about right here, we have a value 5. So that's 2, 4, 5, 4.1. So this is my local maximum. This is my local minimum. And so now we sketch it in. So it's going to come here from positive infinity. It's going to come down through this point. It's going to have a y-intercept of -15. Then it's going to go through a minimum right there. And then we go back up and we go through the x-intercept. And then we go up to our relative maximum. We come back down through the x-intercept, and then we kind of guess where it goes after that. Okay, so there's our plot. From a pre-calculus standpoint, we'd be able to identify this point, this point, this point, and this point. But we really don't know how far it goes up here, and we don't know how far it goes down there. We'd just be guessing. So that's the whole concept of calculus, is that we've got two additional points, the critical numbers, which are the local relative minimum and maximum, which make it so that our graphical representation of the function is much more accurate. So that's what we're going to be doing in section 6 when we get to it, but right now we're not doing that yet. So the next problem that was on your sheet, same kind of deal. In this case, because you have a positive coefficient in front of x cubed, it's going to be going the other way. So it'll come up like this, and then go down like that, and go up like that. And I think I'm just asking you to find the local minimum maximum for that using the first derivative test. So for the next 4 minutes, get started on that. So you're going to take the derivative of that, and I think I made it so that you can factor it. So you won't have to use the quadratic formula to find the two values of x, which are the critical numbers. You'll find there's some common factor that you can divide the derivative by, so that you can simplify it, and then factor the simplified expression, and that'll give you the right answers. So yeah, so go ahead and then after we finish that, which remember tomorrow we're going to have physics first, and then there's the guest speaker. So for you guys who are not in physics, then we won't have calculus tomorrow. And so for you two guys, you just don't come. For the other people, because you're in the governor's school, I think you still need to come, and then come to the presentation. So from 8 to 9, you can just do some study. You can work on stuff, schoolwork. But the talk is at 9:30, and I think Mr. Graham's expecting everybody to be there. It's in here. And your other teachers, which are you taking biology or chemistry? Yeah. So Mrs. Cole probably. What's that? Yeah, you have to do notes on the presentation. Yeah. So you'll need to be here anyway, but you can just go to the library or something during this class period.